This is McZee. You all will be working on your culminating project today, and technically this is the part two. You'll be analyzing the deflection of the projectile using a magnet. So it's a non-contact force. And so you're going to determine the force on the projectile from the magnet first, and then you'll explain how the size, type, and distance of the magnet affect the course using Newton's laws of motion and your understanding of magnetic forces. And finally, explain how the motion of a projectile is changed by force, including what kinds of forces are involved and how they affect the motion of the projectile based on Newton's laws of motion. So this first sheet that you'll be getting is just kind of the overview. And at the bottom has answers to Culminating Project Part 1, where I deflected the projectile using a coin. And these can be used for the other parts of your project. So you'll also be getting this Unit 1 Culminating Project write-up sheet. And so those answers to the last, at the bottom of the last slide in that sheet should help you with answering these questions for the part 2, which is the magnetic non-contact force deflection. This second part is all about just writing how do the different qualities of the magnet affect the force on the projectile, and information on that is on pages 112 through 115 of your textbook. And then this is your final write-up of just how do forces work, essentially. So explaining how Newton's law of inertia, or first law, relates to the deflection, how Newton's second law and third law also relate. You're going to write a paragraph about each. So basically, in a nutshell, you're going to start with finding out the force from the magnet on the metal ball bearing that causes it to move sideways. So you'll have a calculation sheet where you'll do all your written work for finding out that force. On the back of it is data in case you didn't actually collect the data from the videos on Wednesday. What you'll use this for is determining the average point of impact and also for after deflection. So this point right here, as well as how far that is from this average point of impact without deflection. So the average distance traveled between where it would normally hit without deflection and where it would hit with deflection. This is an example of doing all the calculations and solving for the force using a coin. So this is the contact force culminating project part 1. With all the answers in terms of like how you would find out the force. And I'm actually going to go over that now, hopefully make it easier to understand. I've added some animations in these slides to help. So this is the solution with all the just answers, like figuring out what's the distance it traveled, and then how long did it take was 0.57 seconds, so then I figure out the speed that it moves sideways. And based on that information, I can figure out the force. So I'm going to walk through that right now. So the main thing you're trying to solve for is actually just what's the force of the coin on the projectile. And so there's actually several different steps that you need to go through to find that. The first thing you need to do is determine how far does it move to the side, and then use the amount of time it takes to move sideways to figure out the speed that it moves sideways. And then we assume that it gets that speed all during the time that it hits the coin, so the change in speed happens just during 0.01 seconds, and we use that to find the acceleration. And from there, we find the force. So this is probably a lot to look at if you don't quite get all the steps. So what I'm going to do is go over all the steps right now for this. And you'll be using this to solve for the force from the magnet. So this is the video, or a video, of deflection of the projectile by a coin. So if you want to see that again, I'll play it again really quick. As you can see, it happens very fast. And so this is a diagram of that. The coin is moving forwards, and then it hits the coin, and there's a force sideways, and so the coin or the projectile then moves sideways. And what you were to do before on Wednesday was to watch the video and see the average point of impact after collision with the coin, after deflection, and use that to determine the distance that it moves sideways. So I'm going to go to the next slide here. And so part of this project is being able to analyze what the forces are. So before deflection, the projectile is moving along, and these are the forces on it. There's gravity pulling it down, and the table is pushing up against gravity, according to Newton's third law. And of course, as you can see, those forces are balanced, so they're same magnitude, so they don't affect the motion of the ball at all. And the only thing that does affect it is friction, and as you can see, it's a very small force. And so for the purposes of this project, we're going to assume it's equal to 0. We're pretending it doesn't really exist, because it doesn't really affect the motion that much in the short time that we observe the projectile. So here are the forces with the deflector. The forces from gravity, the table, and friction are omitted. Once again, one, because they're balanced, or because in the case of friction, it's so small it doesn't matter. So we have a force of the coin on the projectile, and according to Newton's third law, the projectile also has a force on the coin back. What we want to know is what the force is from the coin on the projectile. And of course, because they're equal, we'll also know the vice versa, but we just want to calculate what that force is from the coin. And so here's a little animation of movement without the deflector and some analysis. So the forward speed is constant. So as you can see, it just goes in a straight line, and there's zero sideways speed. And we have a point of impact without deflection that you should have written down, or it's also included on the data sheet. So we also have movement with a deflector. So there's zero sideways speed before, but then once it hits, because of the force, it has sideways speed after. So here are the forces, and then the projectile has sideways speed and moves sideways. So we end up with a point of impact with deflection, and since we already know the point of impact without, we also know the distance of deflection. So how far did it move sideways? So to calculate the sideways speed, we just need to know that distance, and we need to divide it by the time it took to travel that distance. So the time between the collision point and the point of impact is 0.57 seconds. And so we're going to get 0.0763 meters per second for the speed. And we're going to use that to calculate acceleration. So acceleration equals a change in speed over time, and that means the time it took to accelerate. So if we think about it, the only time that it's changing its speed is when it's colliding with the coin. And another thing too is the change in speed itself is really just that sideways speed it had, because it had zero sideways speed at the beginning, and it has 0.0763 meters per second sideways speed at the end. We know that the change was equal to that. And the time, we're just going to set it as 0.01 seconds. We're going to just assume that it's 1/100th of a second, a very short collision time, in order to calculate acceleration. That might not be accurate, but for this project, we're gonna pretend. So our acceleration is just that change in the sideways speed divided by 0.01 seconds, and we get 7.63 meters per second. So that's how much the speed is changing over time. And that amount of time is that 0.01 seconds. because after its 0.01 second, after that collision time, it's going to move at a constant speed sideways because hopefully you know there are no more forces acting upon it. So when we want to calculate that force, force is mass times acceleration. So the mass of the object, which was 28.4 grams, we need to convert that into kilograms though, because Newton's uses kilograms. And so we just divide by 1,000 to get 0.0284 grams. I just realized there's a little typo, I'll fix that. And we multiply that by the 7.63 meters per second to get 0.22 newtons of force. So that's the amount of force that we have on our projectile from the coin at impact. And what you all are going to do is figure out what is the force of the magnets on the coin to deflect, magnets on the projectile to deflect it. And that is pretty much your project.